Hi everyone, my name is Vineet along with my team members Shrikant, Aziza and Soumya. And today we are going to talk about sign language translation. So let us start. So this is the agenda that we are going to follow today. And we will be beginning with the problem that we are trying to solve and why is it important. Next, we would be focusing on the data that we have used and what all processing have we applied on top of that. And moving on, we would be showing you the machine learning model that we have applied in the data, and we will be sharing the results. And towards the end, we will be talking about the future scope of the project and what all improvements can be done. Let us start. So the first question comes, what exactly is a sign language? So especially American Sign Language. So ASL is a complete and organized visual language that is expressed by facial expressions as well as movements of hands and torso. And ASL is used worldwide, and it is especially used in the USA and some parts of Canada, along with West Africa and Southeast Asia. One of the features of American Sign Language is that not all words have a gesture associated with them. So in that case, that word is broken down into pieces of alphabets, the 26 English alphabets, and each of the letter is presented with a gesture. Moving on to the next slide. Why do we have to deal with ASL at the first place? So American Sign Language is claimed to be the third most commonly used language in the United States. There are 250,000 to 500,000 users of ASL in the US. But it is very complex. It is difficult for a person who is not trained in ASL to understand what the person on the other side is trying to convey. So this creates a huge employment gap of 22% for the people who have a hearing or speech impairment. And this is also one of the reasons why these kind of people who have hearing or speech impairment suffer from mental health conditions. So solving this problem of real-time sign language translation can bridge so many barriers. So this is a problem that we are trying to solve, and I'll tell you exactly what is the methodology that we have followed. So we got the hand gesture images data set, the ASL gestures data set in the form of images, and which is being converted to columnar data. We have tables of data, and we apply various machine learning algorithms on top of that, which we will be discussing in the future slides. And after that, we have the spoken language as the output of the model. So I would be handing over to Shrikant to talk about the data that we have used.
Thank you, Vineet. So let's start with the data. The first thing is, where does this come from? So we have taken this data from Kaggle, where some researchers have actually converted images to the columnar data, which Vineet has spoken about. So this has around 5,200 rows for ASL. However, we wanted to make sure that whatever we are predicting through this model or classifying through this model would exactly be that and not anything else, any random gestures. So we added a bunch of other sign language gestures as a training for the model, where it can tell that, okay, there is nothing, we are not force fitting any specific gestures. Then I'll talk about the dimensions in the coming slides. We have around 428 dimensions of various hand gestures, and we have 18 words which we consider as labels, because we have also added the 4,853 non-ASL related gestures. We have termed them as UNC, and we added that in our data set. Once we got the data set, after we have broken it down into train, test, and validation data sets, we performed multi-collinearity over this, and then we wanted to do PCA, and for doing PCA, we did scaling, and that was normalization. So coming to the columns, so we are dealing mainly only with the hand-related information, nothing related to torso and other facial expressions. So when we come to the hand data, so we have the broader themes like arm and elbow and the various aspects of it. Then we move to the palm and wrist, which are more animated, and the most animated of all, the fingers. But the thing is, In ASL, it is not just one specific image is like one gesture. A series of images is actually one sign or one gesture. So this data, we were lucky enough to find that they were actually converting these individual gestures, series of gestures, and giving us. So that's why you see start, intermediate, and end. So that is the type of columns which we have. And coming to the classes, the labels, we have 19 of them. And as you can see, there is a high amount of imbalance in the data, even excluding our in self-introduced Ank variable. Then because we have a class imbalance data that was by design, we've actually broken down the data into train, test, using stratification. So whatever proportions you see left-hand side, which is on the whole data, would exactly be the same proportions you see in the train test and validation data sets. So I will give this to now.
Thank you, Strik. So we built heat maps to represent the correlation between various features. So shown in this figure, there is a high correlation inwardly between most of the left-hand related dimensions shown in the upper left of the heat map, and similarly with most of the right-hand dimensions shown in the lower right of the heat map. So this shows that there is actually a significant correlation in between the hands, and there's a less correlation between the hands causing, which is actually causing the multicollinearity. So multicollinearity might be a problem in our modeling process, as we would not be able to distinguish between the individual effects of the independent variable on the dependent variable. So to fix the multicollinearity in our data set, we will perform a dimensional reduction. So before running a dimensionality reduction, we first check the distribution of the IDFs using the histograms. So as you can see, majority of the scatter plots are in a Gaussian distribution. So before conducting the PCA, which is principal component analysis, it's important for us to actually normalize the data, since performing the dimensionality reduction on unnormalized data can lead to a large load of variables with the high variance. So therefore, without distorting the differences in the range of values, we normalize our data set. And this histogram actually illustrates the distribution of the features before and after conducting the normalization. So we can see that there are not any differences in the distribution of most of the columns before and after applying normalization. So to lessen the multicollinearity in our data set, we performed the dimensional reduction technique, which is the PCA. As we said, it's a principal component analysis. So initially, we had to choose the number of principal components to extract from the IDF. That's why we used the cumulative variance. So this plot actually shows how much variance explained in each component. So first we started with 85 and ended up choosing 18 principal components based on the variance explained in this plot. So as you have seen from this plot, that with a 0.95 cutoff, the principal component explains the maximum amount of variation from the square root of 7,000 IDMs. So then we actually performed the PCA on the train set, and then we fit it on the test and validation data set. So I will give the floor to Soumya. She'll be discussing the modeling process for our data set.
Thank you, Aziza. So before starting with the modeling and the results, I would like to explain you guys the accuracy and F1 score calculation for multi-class classification. So for this one, we have chosen a random of 3 classes, and on the rows, we can see the actuals. The predictions are there in the columns, and to calculate the accuracy, we'll sum up the values in the diagonal and divide by the total. But for the F1 score, it's a little different. In F1 score, we calculate precision and recall for each of the class. But in this one, we are calculating for each of the class and summing up and dividing by the total number of classes, that is 3. And this method is known as macro. We could have gone for other methods like micro and weighted, but we have a class imbalance. So as to give equal distribution for each class, we are using the macro method. Yeah. This is the models and the results. So the models that we used for our sign language interpreter. As you guys can see, we are not getting a good result for knife face because the basic assumption that there is no independence between the dimensions given the class. And there are some cases where signs are clearly overlapping between the individual classes. And for multinomial logistic regression, it is not giving a good result because it is a linear model. And that is what we can say that one of the reasons why it is not giving a good result. K nearest neighbor, we are not really sure why it is not performing well. SVM is performing pretty decently. It's just that random forest and neural networks are outperforming it and giving the best F1 scores. We have also attached the collab worksheet, which has the data pre-processing, the model, and the accuracy results. Next, we have our NN model architecture. So in this one, we are choosing 18 principal components as the input and passing through 1024 hidden ReLU layers. The output that we are getting to convert it into appropriate probabilities, we are using softmax. We are also using a dropout layer. And for the loss function, we are using cross entropy, and the optimizer is Adam. Yes, and moving on, this is the confusion matrix that is on the test set of the neural network. In this one, you can see there's an overwhelming value for the ANC. All the classes are giving us a pretty good result, except for hello, which is not performing that well, just because hello is a common in many of the sign languages, although this error can be penalized while we run the model. And so this is the entire neural network architecture. And the future scope of this project is like we could go for a sentence-based system. So currently we are working on a word-based system, but we would like to extend it into a sentence-based system. We also want to integrate Leap Motion sensor and take the image data from Leap Motion sensor and implement it with our model. Lastly, we would also currently we are not using audio. So we would also like to use the off-shelf speech synthesizers to translate in real time. So these are the three things. Thank you. I hope you like the presentation.